Welcome back to Math 130, Applied Algebra and Trigonometry. Today we're going to turn a corner in our studies and talk about the law of sines. On a side note, I apologize for the awful vocal fry you've had to endure this semester. Hopefully my voice will recover during the summer. So far, we have always been relying on right triangles to solve vector addition problems, which is fine. You can always break a vector into its components. But could there be another way to deal with this? Is there a way to do this without finding the x and y components of each of those vectors? Yes, there is. And we're going to start talking about ways to do that today. Today we're talking about the law of sines. The law of sines lets us deal directly with oblique triangles like this one. An oblique triangle is simply a triangle that is not a right triangle. You need one more definition. To solve a triangle means to find the measures of all three sides and all three angles. So I hope you remember your geometry because you're going to need it. Also, when we say solve a triangle, you're going to be finding the missing parts. You will be given some parts to start with. In fact, you must know at least 3 parts, and one of those parts must be a side. Why? Here's an example. Here is an equal angular triangle. All of the angles are equal to 60 degrees. But it is also true that this triangle has all angles equal to 60 degrees. And this triangle has all angles equal to 60 degrees. Okay, it would if I drew it correctly. And this triangle also could have all angles equal to 60 degrees. We don't know the lengths of the sides if all we have are angles. If we have even just one side, we can solve for all of the angles and all of the sides and pinpoint exactly what triangle it is. There are 4 combinations of 3 parts of a triangle with which we can start and actually solve the entire triangle. We could have 2 angles and 1 side. We could have 2 sides and the angle opposite one of them. We could have 2 sides and the included angle, in other words, the angle which is formed by those 2 sides. Or we could have 3 sides. In your geometry class, you probably developed a shorthand for these, such as 3 sides would be side, side, side. 2 sides and the included angle would be side, angle, side. 2 angles and 1 side be angle, angle, side, or angle, side, angle. Right? And 2 sides and the angle opposite of one of them would be side, side, angle, or if you reverse those letters, ASS, which you were not allowed to use in geometry and you're not allowed to use in polite conversation, which is one way people remembered that they could not use it in geometry. However, we're not trying to prove triangles congruent. You still cannot use ASS, angle side side, or side side angle, if you're trying to prove triangles congruent. However, if you are trying to solve one triangle, you can use it. And as we learn to do that, you'll see why we cannot use ASS to prove triangles congruent. We will be discussing different ways to use these combinations to solve triangles. What you'll need to know for today is that we will use the law of sines to solve the first 2 combinations, and we will use the law of cosines to solve the last 2 combinations. Today, we're going to be working with the law of sines. Here's an example of a triangle that could be labeled triangle ABC. The triangle is named by the letters of its vertices or angles, and the sides opposite those angles, instead of being labeled with capital letters, are labeled with small letters. And the way I write my small c so you can tell them apart in my handwriting is to make it cursive. So triangle ABC represents the general, or generic if you prefer, ABC triangle that is oblique. And we can form ratios from the different parts of this triangle, such as the ratio of the side A over the sine of angle A. And the law of sines tells us, we don't have time to go into the development of the law of sines, but it tells us that if we set up that ratio, we can also set up an equivalent ratio that is side B over the sine of B, and another ratio that is equal to both of those is the side C over the sine of the angle C. Let's look at a less general case now. We'll look at case 1, which gives you two angles and one side and asks you to solve the rest of the triangle. So here are the two angles and the one side. I recommend that as you're working through these, if a diagram is not given to you, please go ahead and draw the triangle so you can see what you're working with. I also recommend that you move out to the side and you make a chart with a place for each of the sides and each of the angles, and the ones that you already know filled in. The ones that are blank are what you need to completely solve the triangle. I have written the law of sines up at the top of the page, so let's see if we have any of these ratios already in place. Do we have a side and its opposite angle? If you look at the diagram or if you look at the chart, there is no row on the chart that's complete, and there is no angle and opposite side in the diagram itself. So we need to do a little work first. But thankfully you know how to subtract. And since the sum of all the measures of the angles of a triangle equal 180 degrees, if we take 180 degrees and subtract from it the angles we already have, then we can find the measure of angle B. And there it is, 34 degrees. Now that we have a pair shown here and shown here because that's the side opposite this angle, now that we have that information, we can form a ratio of the length of side B over the sine of angle B. And now you can choose to solve for either side. However, I would recommend you go with the largest angle that remains first, because when we go to the law of cosines, that will be a pattern that you'll need to follow. So let's look at, here's the largest angle in our triangle, 120 degrees, and that is angle C. So above that, we will be looking for this side C. And I should have written those in there. Now the sides are labeled A, B, and C. All right, so at this point, we're just going to follow what you have done many times before. You're going to cross multiply. Okay, so on the left-hand side, let's put C times the sine of 34.0 degrees equals 3.07 times the sine of 120 degrees. On the left-hand side, we have C times the sine of 34 degrees. So to isolate that C, we're going to divide by the sine of 34.0 degrees. On both sides, do unto one side as you would do unto the other. That means that these sines will cancel. They will not on the other side. So we have C equals 3.07 times the sine of 120 degrees divided by the sine of 34.0 degrees. And now it's time to turn to your calculator. And we find that the length of angle C is 4.7545, blah, blah, blah. Or, how many significant digits do we need? 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. Oh, nope, only 3 though. 4.75 is the length of side C. So we have found our second part of the puzzle. We have one more to find. We need to find the length of side A. We now have 2 rows filled out on our chart. We have 2 pairs of side and angle. However, the ratio of side C and angle C contains a good deal of rounding error. So we're going to avoid using what we have calculated. And we want to use instead as close as we can get to the original numbers we were given, which would be the combination of side B and angle B. So we set up that ratio, and we set it up equal to a ratio with the angle that we know on the bottom for angle A, and we are going to be solving for side A, and we cross multiply. That gives us A times the sine of 30.0 degrees on the left. That's a multiplication, so we will divide by the sine of 34.0 degrees on both sides. So at this point, we have isolated A. Now we have to refer to the calculator. So here's approximately what you should see on your calculator, and when we round it, we get A equals 2.41. We have filled out this chart. We have solved the triangle. We will look at how this can be applied to addition of vectors later, but right now I just want you to become very familiar with using the law of sines. And I'd like to present another example of this to you, but I will save that for the next video in this series. Please look for that.